speaker is Professor Vannice, who is a distinguished professor of engineering at Penn State University. He got his PhD in Stanford University in 1970, worked as a postdoc at Southern Oil in the same year, and he worked at Exxon from 71 to 76. And in 76, he joined Penn State University. He's a pioneer in the SMSI and all various areas. As you know, he is also an editorial board of the Journal of Catalysis, and he has done extensive work in catalysis. So here I present you Professor Vannice.
Thank you, Stephen. Good afternoon, everyone. Your challenge this afternoon is to stay awake after lunch. I don't know if I will help you do that or not, but I will try. In view of the schedule, as far as the talks, I actually reduced my talk down from what I had planned before I left with a different time commitment. I'm going to talk about low temperature CO oxidation, and I'm going to focus primarily this afternoon on our most recent work dealing with gold titania catalysts and their use for low temperature CO oxidation. Originally I was going to include a little bit of work about our work with CO oxidation over palladium and copper, based on the work of Dr. Choi, who worked with me in my lab. That would be rather limited. Most of the work was done by Sean Lin. I just want to mention to you in this case that gold catalysts have been found fairly recently to be quite active for low temperature CO oxidation. The initial work was done by Haruta and his group in Japan, and in their study of gold dispersed on various oxides, they found the most active oxide in that case was iron oxide. And gold dispersed on iron oxide was a very active system. Subsequent to that, working with a NASA group, Professor Hoffman at the University of Florida has been conducting work dealing with gold dispersed on manganese oxide, non-stoichiometric manganese oxide. This catalyst system is also very active, more active than platinum on tin oxide, and is also active at temperatures below room temperature. The work I'm talking about is gold and titania, and we did not start this program based on this previous work. Our work actually began about the same time as the work in Japan, and we started the work really for completely different reasons in examining gold and titania. I have to admit, we had no expectation it would be active, but there were reasons that we did want to examine it. Now, I've summarized essentially a tremendous amount of work based on CO oxidation over palladium and copper in this slide, which I think is the most pertinent related to the work I want to discuss this afternoon. Both of these metals, after reduction, are quite active for CO oxidation. Palladium in particular has behavior that's indicative of the noble metals in the group 8 family. Copper catalysts, our catalysts were reduced, but in some cases copper oxide in the original state also has activity for CO oxidation. If you look at these catalysts, you get activity patterns like this. Keep in mind now our greatest interest is going to be focusing down in this region, which is relatively close to room temperature. These catalysts have can have relatively steep activation energies, ranging in this case from 11 kilocalories per mole over palladium to 17 kilocalories per mole over copper on aluminum. There are some cases under certain conditions with palladium that the activation energy can become even higher and approach 20 kilocalories per mole. Now I point this out because these catalysts can work quite effectively at higher temperatures, but due to this activation energy they drop off rather markedly as you move to room temperature conditions. Now, we started looking at gold and titania primarily because we had been examining gold and titania for hydrogenation reactions. I won't go into why we were looking at it, but we found it was a completely inactive catalyst for hydrogenation. To try to remove the possibility that one reason for this might be an overlayer of titania covering the gold surface, we thought we would examine some other reaction for which it might have some activity. If one looks at the literature, originally at the University of Michigan about 10 or 15 years ago, Professor Paravano had shown that oxygen would adsorb on gold at higher temperatures. Subsequent work by Johannes Schwank verified that oxygen absorbs in gold, and he looked also at gold dispersed in titanium. We had just finished this study with palladium and copper. The system was set up, so I asked my student, let's just use that very quickly to see if gold might have any activity for CO oxidation. We found a number of interesting things here. Surprisingly enough, if you just disperse gold and silica using gold trichloride, gold on silica has activity for CO oxidation at low temperatures. The activation energies are rather low, and we admittedly don't completely understand this, this pattern, this behavior of the activity, but at lower temperatures you can conduct CO oxidation over gold, albeit at rather low activities. In preparing the gold and titanium catalyst, if we do so and give it our typical low temperature reduction, which is 200 degrees centigrade, this is a terrible catalyst. It has very little activity, essentially no more activity than the pure titanium, and it's only at higher temperatures that some incremental activity begins to develop over this type of system. I show you the background. If we just use pure titanium, at low temperature it's essentially inactive. The pure titanium itself has a low level of activity when it's used at higher temperatures. This has already been reported in the literature. The interesting thing we found in this case was when we gave this catalyst a high temperature reduction at 500 degrees centigrade. This is just the standard Exxon SMSI pretreatment. We found that the activity jumped markedly in this case, well over an order of magnitude, and it became significantly more active than the gold and silica. However, we found that once we took it above 100 degrees centigrade, the catalyst deactivated irreversibly, and we could not track the high activity back. To try to understand this in somewhat more detail, we looked at different pretreatment conditions. And I think the most important thing that I want to point out here is to show in this case, this was the data from the preceding slide that was the most active catalyst system. And again, as we got above 100 degrees, it deactivated irreversibly, as shown here. Now, interestingly enough, if we took this catalyst and gave it a high temperature reduction, 500 degrees, we followed that with a calcination in 10% oxygen at 400 degrees, and then re-reduced the catalyst at 200 degrees, we enhanced the activity significantly by close to an order of magnitude. We now had an extremely active catalyst flowing under these conditions, 5% CO, 5% oxygen, the balance being helium, at room temperature, or at least at 40 degrees centigrade. That was room temperature in our laboratory that morning. Our air conditioning wasn't working. We achieved, under those conditions, 40% conversion of carbon monoxide at 40 degrees centigrade. Most interesting about this system, however, is that we could transverse this same temperature region. In fact, we went up to well over 100 degrees centigrade. And upon cooling back down and retracing the activity, we had lost no activity whatsoever. The red points are going, or the black points are going up in temperature, the red points are coming down in temperature. Again, of some interest, you can see that by the time we were at 100 degrees centigrade, we had essentially achieved 100% conversion. Now, this obviously is not the proper way of conducting experiments to make good kinetic measurements, but it did at least verify to us that this was a very active system which could remove carbon monoxide quite effectively at relatively high pressures. For comparison, I took that earlier slide for palladium and copper, and if we were to plot those activities on this same slide, at 423 Kelvin approximately, palladium and copper would have this activity on a turnover frequency basis. On an activity basis per gram of catalyst. At room temperatures, these catalysts would have an activity down here. So we're talking now about approximately 1, 2, perhaps close to 2.5 to 3 orders of magnitude activity in the low temperature regime. We have subsequently examined this system further. We have an ongoing program, and I included some of the most recent results from the current student working on the program. And I've tried to summarize these results on this slide. When it is possible to do so, I have tried to report activities in turnover frequency. In the cases where this information was not available or has not yet been calculated, that representation is not included. The most common comparisons for activity in this case are approximately 5% oxygen, 5% CO, or about 1% CO and 0.5% oxygen. The reason for the lower values is that these are quite representative of the CO and oxygen levels that exist in the orbiting CO2 lasers around the world. And the lifetime of those lasers, which are used for meteorological studies and weather forecasting, is determined by the degradation of the CO2. And that's the requirement that NASA has for a low-temperature CO oxidation catalyst for recombination to maintain the lifetime of these orbiting CO2 lasers. Under those conditions, these are fairly representative of what might exist in that particular system. Now, if we look at, again, the earlier work of Haruta and his iron oxide-supported gold catalyst, he in that case measured the iron particle size with TEM, and he used a co-precipitation technique to get very small particles. He found his average gold particle size was less than 40 angstroms. Using that as a basis to estimate a turnover frequency, he obtained, we obtained this value. In all cases, in this column, I will be reporting activity per gram of gold. And needless to say, trying to measure the surface area of gold is a difficult thing to do, particularly if you want to do it quantitatively. Now, if we take the gold and manganese oxide of Hoffman and co-workers under these conditions, we can now compare the activity here. This is all at 40 degrees centigrade. We get an activity here of about 3 versus a value of about, it's at least 21. It could be even higher. We could not determine this quantitatively from the data in the paper. Here are our catalysts up here. This is the catalyst I reported earlier after the special treatment that gave the high activity. And we can see on this basis that we have a very active catalyst per gram of gold. And from our X-ray diffraction data and other TM values, we know we have large gold particles. They are close to 300 angstroms. If we take these values and estimate turnover frequencies, our catalysts are at least as good as, and substantially higher, more active than the best catalysts that have been reported in the literature. We found recently in an obscure meeting in Europe that we just became aware of that they had reported also gold and titania. This is not in the open literature, but that catalyst was quite active. And again, taking the data from their paper, they had about 100 angstrom particles. We can estimate a turnover frequency and an activity per gold that is really quite comparable to the values that we had measured in our system. Most recently, we have looked at the catalyst represented here. We prepared another batch of the 2% gold and titania. We have found that this catalyst is even more active, as shown here. It also has extremely good activity maintenance. As of the time I left, we had done partial pressure studies and Arrhenius runs with no loss in activity. This catalyst will convert CO at ice water temperatures and probably below. It's just we have not yet gone below 0 degrees centigrade. Just as I left, we are now looking at the effect of gold loading. We have gone down to a 0.4% gold and titania. Even at this much lower loading, we're still achieving quite high activities per gram of gold. So it appears in this case that one has some control over the activity by monitoring or controlling the amount of gold. We have not yet determined particle size here. I don't know exactly what our turnover frequency is going to be, so I've left those blank. I think that the sum of this set of data, I think, is to try to convince you that indeed gold on titania is a very active CO oxidation catalyst. Number two, to the best of my knowledge, this is the first titanium-supported metal system which might be considered in the perspective of metal support effects that has shown an activity enhancement in a reaction other than a hydrogenation reaction. Now, interestingly enough, we've done chemisorption measurements on these systems at room temperature to try to get some idea of the chemisorption capacity. It is very low. If we look at oxygen chemisorption, this upper line, we find that there's a very small irreversible uptake of approximately, well, it's very low. It's less than 1 micromole per gram. And it doesn't make a big difference whether it's on the active catalyst that was calcined or the very inactive catalyst after a low temperature reduction. In both cases, the oxygen uptakes are low, and clearly the small increase here cannot explain the 3 order of magnitude enhancement that was achieved by this particular pretreatment step. If we look at carbon monoxide chemisorption, we've looked at this as a function of pretreatment on a gold titania system. And basically I can sum these results up by saying that, first of all, putting the gold on the titania has essentially no effect on the chemisorption capacity. The closed symbols and the open symbols for each run represent the initial chemisorption, evacuation, and reabsorption. It's very clear, I think, in this case that essentially all the adsorption is reversible. It follows very nicely a Langmuir isotherm. The only significant difference that we find with chemisorption of CO at room temperature is for silica. And we find that for gold and silica, the uptakes are extremely low and they follow Henry's law behavior. So I think we can conclude that there is a difference in adsorption between titania-supported gold and silica-supported gold, and that the adsorption on the titania-supported system is markedly higher, although it is completely reversible. We've initiated some partial pressure studies. Some of these have just been reported, others are continuing. I've included them all here essentially. If we just take our data and we fit it to just a simple power law rate expression, we can find here that with this simple expression, we go over a fairly wide temperature region of about 80 degrees centigrade, we find that the partial pressure dependency does not change markedly. It's around 1/2 or lower. It's between 0 and 1/2 based on the carbon monoxide. As far as oxygen is concerned, the partial pressure dependencies again are low, but positive, as you can see here. So in this case, intriguingly, both adsorption dependencies are low and positive. This is in marked contrast to the dependencies on palladium and copper. In one case, it's first order in one reactant and negative first order or negative dependence on the other reactant. So we're getting a very different dependence upon the reactants in these titania-supported gold catalysts. We have attempted some initial modeling studies. These are by no means conclusive, and so I suggest that we just view them as kind of a guidepost at the present time. Regardless, perhaps the most significant aspect of this is that if we take our kinetic data, our partial pressure studies, we cannot fit our mechanism, any mechanism, by assuming dissociative oxygen adsorption. We cannot fit the data, and we get completely meaningless adsorption parameters in our Langmuir-Hinshelwood model. So if we relegate ourselves to a Langmuir-Hinshelwood type of approach, the assumption of dissociative oxygen adsorption is not applicable. And we must assume that we have a reaction between adsorbed CO and O2 molecules. In addition to those, we have looked at other models that also had to be discounted. And at this time, the only model that seems to the only models that seem to fit must involve a reaction between adsorbed CO molecules and adsorbed O2 molecules. We cannot distinguish, as I'll show you in a moment, between the assumption that we have two types of active sites, one which absorb oxygen, the other which absorb CO, or if we assume one type of site which is subject to competitive adsorption of the two reactants. Either of these two fit the data equally well or equally poorly, as you are going to see in a moment. There is some scatter in the data, but at the present time, our best fits are coming from the assumption of molecular oxygen involvement. At these three higher temperatures, these are the data points at three different temperatures in blue, red, and green. This represents our best fit, assuming either competitive or non-competitive adsorption. As you can see, the two models are roughly commensurate with each other. If one takes the overall behavior, however, at the present time, we tend to prefer the non-competitive adsorption model. And we get a little bit better fit with the solid line model than with the dotted line. However, I don't want to be dogmatic about this because, as you can see, the scatter in some of these fits is rather noticeable. That was for the dependence on CO adsorption. If we look at the dependence on O2 adsorption, we see this behavior. We get a reasonably good fit at the higher temperature, not a bad fit at the lower temperature, but the fit at the intermediate temperature is not particularly good. One comment I'll make here with this particular set of runs, we were fighting to some extent some deactivation complications for which it was somewhat difficult to correct. That might have some effect on this. But regardless, we get reasonable, if not good, fitting with that particular type of model. Now, one last piece of information, we were asking ourselves what might account for this, what parameters might be affecting the behavior. We did do chlorine analyses of these catalysts. We haven't completely determined what this means, but it's interesting to note with gold chloride, of course, we start with a chlorine to gold ratio of 3. For all three catalysts that were exposed to high temperature reduction, regardless of whether it was silica or titania, we ended up with a chlorine to gold ratio of 1/2. Now, of course, there were differences in activity among these three catalysts, and this was our best catalyst. But it appears under these cases that we cannot get all the chlorine out of the system. For the very inactive catalyst, as shown here, we removed much less chlorine. We only removed about half of it. And we are at least accepting the possibility at this time that part of the reason of the low activity for the low temperature reduced sample was due to the fact that we had large amounts of residual chlorine remaining in the catalyst. Now, in my last slide, I'm just going to perhaps speculate and throw some possibilities out regarding what might account for this high activity. We're planning to do some in situ infrared studies in the future and some additional studies to try to clarify this to a greater extent. But if we look at some of our current possibilities, we have not yet determined whether or not residual chlorine might be responsible for the low activity. It's a possibility. But without question, the amount of chlorine in the catalyst cannot explain the high activity. Also, the gold crystallized size does not appear to explain the activities of any of the catalysts that I've talked to you about, whether they were our catalyst or whether they were prepared in other laboratories. For instance, we found that our catalyst, which had about 250 or 300 angstrom particles, we had comparable activities compared to the co-precipitated catalyst prepared by Haruta, which had much smaller particle sizes. So at this point, we cannot attribute these activity dependence, these variations in activity, to a crystallized size dependence of gold. Our current guess, and perhaps it's stronger than a guess, but our current model, we feel, probably is going to invoke interfacial sites that are created at the interface in these gold titania catalysts after the appropriate pretreatment. We don't understand completely how these pretreatments affect these interfacial sites, but our thinking is based upon what I've told you. We're speculating, because of the adsorption capacity, the role of titania to facilitate this is to weakly chemisorb the carbon monoxide. You saw it had a much higher chemisorption capacity than the silica. Our thinking then is that on small gold crystallites, oxygen is activated on the gold. And if these sites exist in proximity of each other, so we have activated oxygen on the gold, chemisorbed CO sitting on the titania, we then believe that this might account for the higher activity. One final comment here that's very interesting. it becomes, I think, rather clear in these studies that very small gold crystallites behave markedly differently than gold single crystals. Bob Vannice has shown very clearly on gold single crystals that oxygen does not chemisorb on bulk gold. But both we and Paravano and Schwank have shown that very small gold particles will chemisorb oxygen, certainly at higher temperatures. And I think this work indicates that gold can activate oxygen under appropriate conditions. Thank you very much.
Okay, we have at least 5 minutes for discussion.
Simon from Southwestern University. I have two questions. One is, have you ever tried to monitor any changes in the surface by these treatments using techniques like infrared or any XPS or anything, or QPD or anything?
The surface area of what?
No, the changes in the adsorption properties of the catalyst, or what kind of, or what types of molecules are adsorbing on the surface by monitoring it with any techniques like infrared.
No,
That's one question. Let me finish. The second question was, are you sure that this reaction is occurring on gold? Isn't there any possibility that titanium itself is working as a catalyst for that?
With regard to the first question, the only characterization we've done so far is BET and chemisorption measurements. As I mentioned, our current program involves beginning some in situ infrared studies. So we are trying to determine what species exist and if we can identify them. So we're moving along those lines. In regard to the second question, certainly pure titanium is not a good catalyst. The question is, if the entire reaction is occurring on the titanium, why do you need the gold? Because palladium and gold and platinum and gold and other metals and gold are not good CO oxidation catalysts. There's something unique about gold. And the second part is that the second aspect is you can take any reducible oxide, iron oxide, manganese oxide, and apparently properly, when pretreated properly with gold, these become very active low temperature catalysts.
So the chance may be that the gold is doing something to promote the activity of titanium. You showed a slide showing that titanium itself has some activity at high temperature.
Yeah, yes, but far above what we're...
Okay, at high temperature.
Yes.
And now, by adding gold, you may be promoting the activity of titanium so that it shows high activity at low temperature. Isn't it possible?
Yes.
Troy from Yukon. You mentioned in your presentation, the great concern is that the amount of absorption of CO and oxygen from on the titanium or gold, and but you computed the equilibrium constant from your model, and probably you can compute it. You can calculate the amount of absorption of CO and oxygen from your modeling study. And, have you checked how much coverage of CO and oxygen you can get from that modeling?
Yeah, I know what you're saying. That's not a bad question. We haven't done precisely that. We've done something similar in the sense that we've taken our kinetic equilibrium absorption constants and we've extracted values for the entropies of absorption and the enthalpies of absorption. And the only thing we can say about those is they are physically meaningful and they're low. Both of which would be very consistent with the constraint that you have reversible absorption at room temperature. They're low enough to allow that to be achieved. What you're asking, I think, is have we taken these values from here and calculated just an equilibrium absorption, I suppose? I don't think so. But I think the student did estimate uptakes based on the two, and they were comparable. Okay. I mean, in other words, you would get coverages from this, uptakes that would be close to what we measured under equilibrium absorption conditions.
Okay, the other question is that, if I remember correctly, the activation energy from the experimental result is lower than the values from your modeling. So can you explain that the difference?
Yeah, thanks for reminding me. I forgot to mention that. The activation energies that we see for these gold titanium catalysts over the low temperature region between 0 degrees centigrade and 100 degrees centigrade is somewhere between 5 and 10 kilocalories per mole. It is much lower than the activation energies associated with the noble metal catalysts and even with copper. But the activation energies are quite low.
And the last question.
Yeah. Alex Bell, University of California. About a year ago, we did some experiments with a rhodium foil onto which we deposited submonolayer amounts of titanium. And in that case, when we ran the same reaction, we found a fall off in the CO oxidation activity that was linear with the amount of rhodium that we blocked. But I don't think that's inconsistent with what you're observing. I think the difference is that on rhodium, CO binds very tightly with a maybe 20 or more kilocalorie heat of absorption. Your heat of absorption for CO from this model is about 5 kilocalories. And so probably the reason that your system works is exactly because gold is so poor for chemisorbing